an amazing discovery by NASA to tell you about. The space agency says it has found what it's calling Earth's cousin. It's the most similar planet to our own they've ever found. In April 2025, a subtle dip in the light of a faint red star reveals something unusual. Astronomers report in the data a potential biosignature from a world more than 100 light-years away, a fingerprint of dimethyl sulfide in the spectrum of the atmosphere of the exoplanet K2-18B. On Earth, DMS is a gas produced almost entirely by life forms. If this detection is confirmed, it would be the strongest hint yet of biological activity beyond our solar system. The news made headlines all over the world. Has the James Webb Space Telescope detected the chemical scent of life on a distant planet? As space's silence reveals, a new chapter unfolds in the search for life. However, before making any conclusions, we must comprehend the stage where this drama is unfolding. The planet K2-18B itself. What kind of world could harbor such an enticing signal? Our discovery is the first step on the journey to understand the nature of this intriguing Exoplanet.K2-18B. It's a far-off exoplanet that orbits the cool red dwarf star K2-28, located about 124 light-years from Earth in the constellation of Leo. This alien world was first discovered in 2015 by NASA's Kepler Space Telescope during its K2 mission, when astronomers noticed the planet makes periodic orbits around its star, causing tiny dips in starlight. From those dips, they deduced the planet's basic properties. It has an approximate radius 2.6 times that of Earth and a mass around 8.6 Earth masses, placing it in the category of a sub-Neptune or mini-Neptune. It's larger than Earth, but smaller than Uranus and other ice giants like Neptune. Despite its size, the planet orbits within the habitable zone of its star, the region where temperatures may allow liquid water to exist. A year on K2-18B only lasts about 33 days, which is rather short. But thanks to its close orbit around a dim star, the planet receives roughly the same amount of light from its red sun as Earth does from our own. The estimated median temperature is about 117 degrees Celsius, or 265 Kelvin, potentially Earth-like, depending on the greenhouse effect. It's worth noting that K2-18B stood out early on due to its location and structure. In 2019, using the Hubble Space Telescope, scientists detected water vapor in the planet's atmosphere. It was the first time water vapor had been seen on a small exoplanet in the habitable zone, a discovery that sparked global excitement. It confirmed that the planet could have a substantial atmosphere containing water, a vital component of life. This discovery placed K2-18B on the map as a prime target for further observations. Could it be an Earth-sized version, or something more exotic? Soon, all evidence suggested a brand new class of planets, high-sign planets. K2-18B doesn't quite fit into the usual categories of rocky, Earth-like planets or gas giants. Scientists believe that, instead, it may belong to a recently proposed class of exoplanets known as high-sign planets. The term high-sign is a portmanteau of hydrogen and ocean, coined in 2021 by a team at Cambridge University to describe planets covered in oceans and shrouded in hydrogen-rich atmospheres. These worlds are larger and have a higher mass than Earth, possibly around 2.6 times larger than Earth's radius and up to 10 times its mass, yet could still offer temperate surface conditions. K2-18B fits this profile almost perfectly. It's been dubbed the leading high-sign candidate. What might a high-sign planet look like? The concept describes a world with an ocean hundreds of miles deep, surrounded by air dominated by hydrogen and possibly helium. An atmosphere like that is much lighter and less dense than Earth's nitrogen-oxygen blend, allowing it to extend farther into space. A thick hydrogen blanket could act as an insulating layer, possibly helping retain oceanic heat. High-sign planets could orbit a variety of stars. Astronomers consider sub-Neptunes of this size to be extremely prevalent across our galaxy. Yet, for a long time, these mid-sized planets were not a focus of study. That is now changing. potential. Habitability of such planets is prompting astronomers to rethink the boundaries of habitability. According to Niku Maiden, an astronomer at Cambridge University and the lead author of the paper announcing the discovery. Such findings underscore the importance of thinking about different habitable environments. Traditionally, the search for life on exoplanets has focused on smaller, rocky planets. But the larger Hycean worlds are significantly more conducive to atmospheric observations. In other words, although these planets may resemble mini Neptunes more than Earth, they might offer the best chances for spotting evidence of life, since their dense atmospheres are easier to probe across light years. The idea of Hycean planets has opened new possibilities for our imagination to truly understand the character of K2-18B. We must study its structure and atmosphere as closely as the data allows. We can infer the internal structure of this planet from its size and density. With a density of about 0.1 grams per cubic centimeter, K2-18B is neither a gas giant nor solely rocky. The best models suggest this is a layered world. At its center, there's likely a silicature-rich rocky core with metals. Above it, pressure forces water into exotic forms, a mantle of high-pressure ice. And above this solid mantle, there could be a vast ocean of liquid water, if the circumstances are right. All of this is surrounded by a dense atmosphere rich in hydrogen and possibly helium. Essentially, K2-18B could be a world with an ocean and no land. A planet of global seas under a thick, hydrogen-dominated sky. Whether or not this planet has a liquid ocean depends on the thickness of the hydrogen atmosphere. If the atmosphere is too thick, the water beneath it would be subjected to crushing pressure and heat, possibly forming a supercritical fluid, a true liquid or gas, but an environment likely hostile to life. On the other hand, if the hydrogen layer is relatively modest, the water layer could maintain conditions more similar to Earth's, suitable for life. This issue was discussed during early research stages. Initial estimates suggested that water on K2-18B could exist in a hot, supercritical state without a distinct ocean surface. However, later analysis, especially using new JWST data, indicated that the atmosphere might not be too dense. There are signs pointing to a real ocean atmosphere. Interface, in other words, an actual liquid water ocean beneath the gas. One of those signs is the absence of ammonia. The presence of ammonia is expected in a hydrogen-rich atmosphere, unless it has somewhere to go. A liquid ocean would be the perfect sink for it, since ammonia dissolves easily in water. JWST detected methane and CO2 in the air on K2-18B, but very little ammonia, which supports the hypothesis that a water ocean may exist beneath a hydrogen-rich atmosphere. If the ocean does exist, it may be very deep, much deeper than any on Earth and possibly warm, depending on heating from the planet's interior and atmosphere. The ocean may be hidden under thick clouds, where air, moist and full of hydrogen, meets the cooler layers of space. As mentioned earlier, beneath this ice ocean, pressure would ultimately cause the water to freeze into ice, possibly preventing direct interaction between the water and the rocky core. This has implications for life without. The circulation of minerals on the ocean floor and the ice layer may limit nutrients, potentially posing a challenge for any biological activity. However, life in such a world might resemble Earth's extremophiles from the deep sea, which use energy from chemical gradients or faint filtered starlight from above. In the oceans, microscopic marine plankton, specifically a few species of bacteria and phytoplankton, create a compound known as DMSP, which they use to regulate their cells. When these organisms die or are consumed, DMSP breaks down and releases the gas DMs. Therefore, the majority of DMs in Earth's atmosphere comes from marine phytoplankton. There are virtually no significant abiotic non-biological sources emitting this gas into the air in large quantities. For instance, earthquakes and hydrothermal Vents release a wide range of sulfur compounds, but not much dimethyl sulfide. Therefore, on Earth, if you detect DMs, you are essentially detecting signs of life. Consequently, DMs has been proposed as a potential biogas that distinguishes exoplanets. It's akin to coming across smoke from a campfire in a forest, which you would immediately assume indicates someone's presence, since fires rarely start on their own. Moreover, this gas in the air only lasts a short time. On Earth, the molecule breaks down under sunlight, typically lasting between a few days and a few years. This indicates a continuous active source is needed to maintain an obvious presence of DMs. If K2-18B actually contains this substance in detectable amounts, it implies that something on the planet is regularly emitting the gas. For astrobiologists, that something could very well be biology in alien biosphere in a hypothetical ocean. Methane, also found on K2-18B, is frequently regarded as a biosignature in its own right. When detected alongside CO2 in the absence of large amounts of carbon monoxide, methane can be produced by microbes. In the case of an exoplanet, methane could also develop abiotically, for example through hydrothermal processes or during the initial formation of the planet. So it's not a smoking gun on its own. However, the combination of methane and carbon dioxide without ammonia is interesting. Some researchers argue that this combination is hard to sustain without biological sources because methane tends to break down via photochemistry unless there's a powerful replenishing source which life can provide. Add to that the tentative detection of DMs, and you get a potentially compelling argument that something biological could be at work. Nonetheless, extraordinary claims require extraordinary proof. At this point, there is not even a confirmed trace of dimethyl sulfide, and scientists are approaching it with a healthy dose of skepticism. Let's look at why caution is warranted and why alternative explanations and challenges must be considered. The rumors about the possibility of DM's detection highlight that the evidence is not yet conclusive. According to the researchers themselves, the signal from JWST data has low statistical significance, about 3 sigma, which means there's roughly a 0.3% chance that the signal is just noise. Statistically speaking, 3 sigma is considered tentative, whereas the gold standard for discoveries is usually 5 sigma, which is equivalent to about a 0.0003% chance of happenstance. In an explanatory note accompanying the Nature news piece, other astronomers emphasized that the team is pushing the capabilities of JWST to its limit with this detection. Exoplanet observation data is extremely complex. We are looking for minute absorption features buried in the noise of a minuscule signal. The rays from a star traversing a thin ring of atmosphere around a distant planet compounded by noise from instruments. In conclusion, this saga highlights a turning point in our search for life on other planets. For decades, the prevailing mantra was to find the next Earth, a twin of our world with a star of the same size, orbit, and type. K2-18B is not comparable to Earth in the conventional sense. It's much bigger, probably doesn't have land, and orbits an entirely different kind of star. In doing so, it has broadened the diversity of worlds studied by astrobiologists. In essence, this distant world's greatest contribution so far is raising more questions about life in the universe. It has shown that our search cannot be one-dimensional. We must cast a wide net from rocky planets around sun-like stars to many Neptunes surrounding red dwarfs, and from biomarkers such as oxygen and ozone to more exotic substances. Imagine, a century or more from now, an Earth-launched interstellar probe equipped with advanced instruments and artificial intelligence embarking on a lengthy journey to this faraway planet. As it nears the K2-18B system, the probe's cameras capture a blue orb lit by the ruddy light of a dwarf star, confirming the theories of our telescopes. It perceives a planet covered with a vast ocean and thick clouds. Upon arrival, the probe could pass through the dense atmosphere, plummeting through a sky painted peach by the red star's light sifting through a cloud of hydrogen. It directly traverses cloud layers, sampling their composition. Fierce winds far more powerful than Earth's could strike the capsule, but at some point, it reaches a vast alien ocean that extends to the horizon in all directions. Dark, endless. Ceilings of clouds obscure the local star, which glows dimly a red flame half the size of our sun, casting a copper gleam across the wave crests. As the robotic explorer submerges in the water, detects a microorganism from an alien ocean, confirming that we are not alone yet. Such a mission is far beyond our current capabilities. At 124 light-years away, the distance is staggeringly vast with today's propulsion systems. For now, we remain distant observers, decoding faint spectra and refining our theories. Spectrum by spectrum, transit by transit, we are gaining a better understanding of this world. Until we can send a distant probe, our vigilant telescopes. We'll keep listening to its hushed whispers so that when life speaks, even from a faraway ocean world, we'll hear it.